Hi, this video is for the introduction of our paper towards high quality and efficient video super resolution via spatial temporal data overfitting. Leveraging the overfitting ability of the DNN to achieve video resolution upscaling has become a new trend in the modern video delivery system. However, a large number of chunks are expected to ensure good overfitting quality, which substantially increases the storage and consumes more bandwidth resources for data transmission. To solve this, we propose a novel method for the high quality and efficient video resolution upscaling tasks, which leverages the spatial temporal information to accurately divide video into chunks, thus keeping the number of chunks as well as the model size to minimum. For video compression, we already have very effective technique like H.264. However, with the development of deep learning, researchers find that we can use SR to implement video compression. The following diagram shows how it works. If we have a low resolution video and the video size is 1 MB, and we have a 2 MB SR model that can make an LR video into HR video. Instead of transferring a 10 MB high resolution video, we only need to store a LR video and SR model. When we need an HR video, we only need to do an inference on the model, and the process is super fast. Now I want to introduce the background of single image super resolution. The pioneer work of SISR is SRCNN. It uses deep neural network to learn a nonlinear mapping from low resolution image to a high resolution image. We also have VDSR, EDSR, WDSR for SISR work. And then I want to introduce the video super resolution. Our previously mentioned EDSR and VDSR model also can be applied to VSR. And we also have EDVR as a VSR method. However, there are some limitations of current SISR and VSR models. These models are trained on general datasets, and we cannot make sure the model could have a good performance on every video on the internet. And the majority of the current SI models are too large to run on edge devices. Therefore, we consider using one model to handle one video by leveraging DNN overfitting property. Although overfitting is not a good thing in machine learning, however, this works in our scenario. We use LR video as training data, and we want our training data can be best super resolved. We call data overfitting DNN as content-aware DNN. NAS was the first proposed video delivery framework to consider using DNN models to overfit each video chunk to guarantee reliability and performance. cvpr splits a long video into different chunks by time and designs a handcrafted layer along with a joint training technique to reduce the number of SR models and improve performance. However, there are some limitations of current content-aware DNN models. Models like NAS and cvpr simply divide the whole video into chunks by time. For long and complex videos, overfitting performance heavily relies on the number of chunks. However, more chunks means more DNN models are required, which is not efficient. Here, we split video into frames and frames into small patches. We evaluate these patches by a general WDSR model and use PSNR to evaluate SR quality. And we can see that there is a clear boundary, which shows that PSNR is strongly related to video content. Therefore, solely division according to time is not efficient and fine-grained. We argue that even in each frame, there is this unbalanced informative data. So we need to reconsider the clustering method. Here we show the overview of our STDO framework. We firstly split video into images and images into patches. We send patches into a general SR model to get a PSNR. We cluster patches according to their PSNR. This method can elegantly divide patches. Typically, similar texture complexity patches will be clustered together. Then we train its trunk with the model and finally assemble it into HR video on user end. We use one model to fit one trunk. Each model will learn a similar distribution, so we have a better performance. Since each trunk has similar data patches, we can actually use smaller SR model without handcrafted models for the overfitting task, which reduces the computation burden for edge devices. Now we want to show our results. For the experiment on 15-second videos, our method STDO show better PSNR than other methods. And the same for the 45-second videos. We test our method on the longer video with more complex tests too. We combine game 45 video and vlog 45 video into a 90-second long video. The result is close to the average value of overfitting these two videos. Compared with industrial standardized method H.264, our method is also much better. Under the same compression ratio, we have higher PSNR. And under the same PSNR, we have much better compression ratio. For the deployment on edge devices, we have higher PSNR and smaller latency compared to both EDSR and VDSR. Compared with different frameworks, our method obviously show better results. And compared with H.264, we can see that the details, for the details, our method is much better and is very close to the ground truth. Thank you so much for your time.